Hi, my name is Samir Desai, and in this video, we'll learn how a change in temperature can cause a system in equilibrium to shift.
Le Chatelier's principle states that when a stress is placed on a system, the system will counteract the stress by shifting its equilibrium. As we previously discussed, things like concentration, pressure, and temperature are common disturbances to a system. While a change in concentration or pressure affects the value of the reaction quotient, the equilibrium constant is unaffected. This is in contrast to the change in temperature, which changes the value of the equilibrium constant, KEQ. To illustrate this concept, let's take a look at an example reaction. Chemists measure the rate at which the product forms. This is known as the reaction rate. The rate of the forward reaction, we'll call this RF, with the F for forward, is dependent on the concentration of the reactants, A and B, times the rate constant, Kf. The rate constant, a proportionality constant, is derived under a constant temperature. This should be intuitive, because we expect a change in the rate of a reaction when heat is added. So the addition of heat will affect the rate constant, and we typically expect an increase in the rate of the reaction. Just like there's a rate for the forward reaction, there's also a rate for the reverse reaction, RR. Similarly, this rate is determined by the concentration of the products, C and D, times the rate constant, Kr. Now, when a system is in equilibrium, then the rate of the forward reaction will equal the rate of the reverse reaction. So these two components here will be equal. Rearranging this equation gives us the following. C times D over A times B is the concentration of the products over the concentration of the reactants. This is the equation for the equilibrium constant. Therefore, Kr over Kf equals Keq. So what does all of this mean? Well, taking it back to the basics, remember that increasing the temperature will always speed up the rate of the reaction, both forward and reverse. And since temperature affects the value of the rate constants, then it must hold true that temperature will also affect the value of Keq. An important point here, if we increase the temperature and see a decrease in Keq, this doesn't mean the reaction is slowing down. It means that the rate of the forward and reverse reaction both increased, but the reverse reaction increased more. And to cover the last 2 points on this page, the change in temperature establishes a new Keq, and the reaction shifts such that Q equals Keq. These 2 points below will help in predicting how the equilibrium will shift when there is a change in temperature. An endothermic reaction requires the input of heat to the reactants. Therefore, think of heat as the reactant, and the equilibrium will shift towards the products. Alternatively, an exothermic reaction releases energy, so think of heat as the product, and the addition of a product will shift the equilibrium towards the reactants. Let's apply this knowledge and predict how the equilibrium will shift in the following questions. For A and B, we need to determine how the equilibrium will shift with an increase in temperature. The first step is identifying whether the reaction is endo or exothermic based off the enthalpies. Once that is determined, we can use the information from the previous slide to predict the shift in equilibrium. The enthalpy in A is negative 1,418 kilojoules per mole. The negative enthalpy indicates that this is an exothermic reaction, so we should treat this like we're adding heat to the products. Adding heat to the products means that we'll see the equilibrium shift left towards the reactants. The enthalpy in B is positive, so we know this is an endothermic reaction. Again, endothermic means we can treat this as adding heat to the reactant side. Therefore, the equilibrium will shift to the right towards the products. Now that we've covered the effects of temperature on a system's equilibrium, you should now feel comfortable with this concept.